In the depths of Princeton University's archives, buried beneath decades of papers and forgotten calculations, lies a mathematical revelation that Albert Einstein discovered but never revealed to the world. This isn't about his famous equation, E equals mc squared. This isn't about relativity or the photoelectric effect. This is about something far more profound and mysterious, a hidden mathematical framework that connects the smallest particles in quantum mechanics to the very fabric of space-time itself through entities called spin-2 particles. Most people think Einstein spent his final years as a stubborn old man, refusing to accept quantum mechanics and chasing impossible dreams about unified field theories. But what if I told you that Einstein actually discovered the key to unifying quantum physics and gravity decades before anyone else even knew such a connection was possible? What if his greatest insight wasn't about the speed of light or the equivalence of mass and energy, but about mysterious particles that literally shape the geometry of reality? Tonight, we're going to uncover Einstein's most profound secret, the mathematical bridge between quantum mechanics and general relativity that physicists have been searching for over a century. We'll explore how particles with a specific quantum property called spin-2 don't just move through space-time, but actually become space-time itself. And by the end of this journey, you'll understand why this hidden equation might be the most important discovery in all of physics. But first, let me tell you about the moment everything changed. Picture this scene. It's 1916, just 1 year after Einstein published his general theory of relativity. The ink is barely dry on equations that revolutionized our understanding of gravity and spacetime. Most physicists are still struggling to comprehend the implications of curved spacetime and gravitational time dilation. Yet Einstein is already thinking about something that wouldn't be fully understood for another century. In a paper that most people overlooked at the time, Einstein wrote about something he called quantized gravitational radiation. He realized that if light comes in discrete packets called photons, then gravitational waves might also come in discrete packets. These hypothetical particles would later be called gravitons. But Einstein understood something even more remarkable about these particles. Something that would connect the quantum world to the geometry of spacetime in the most elegant way possible. Here's where it gets mind-bending. Einstein discovered that gravitons must have a specific quantum mechanical property called spin-2. Now, before your eyes glaze over, let me explain why this is absolutely revolutionary. In quantum mechanics, particles have an intrinsic angular momentum called spin. It's not that they're literally spinning like tops, but they behave as if they have this fundamental rotational property. Photons, the particles of light, have spin 1. Electrons have spin 1/2, but gravitons have spin 2. This might sound like just another quantum number, but the implications are staggering. The spin of a particle determines how it interacts with the world around it, and spin-2 particles have a unique property that no other particles possess. They don't just interact with matter and energy. They literally become the stage upon which all physics takes place. Think about this for a moment. Every other force in nature is mediated by particles that travel through space-time. Photons carry electromagnetic forces through space. W and Z bosons carry the weak nuclear force. Gluons carry the strong nuclear force. But gravitons are different. Gravitons don't travel through spacetime. Gravitons are the quantum fluctuations of spacetime itself. This is Einstein's hidden equation, not a single formula written on a blackboard, but a profound mathematical insight that the geometry of spacetime and the quantum mechanical properties of matter are two sides of the same coin. When Einstein wrote his field equations relating the curvature of spacetime to the distribution of matter and energy, he was actually describing how spin-2 particles emerge from and create the very fabric of reality. Let me show you why this connection is so extraordinary. Einstein's field equations tell us that matter and energy curve spacetime. The more massive an object, the more it warps the geometry around it. This curvature is what we experience as gravitational force. But from a quantum perspective, this curvature consists of countless gravitons, spin-2 particles that collectively create the smooth geometry we observe at large scales. Here's the beautiful part. The mathematical structure of Einstein's equations demands that gravitons have spin 2. It's not a coincidence or an arbitrary choice. The tensor mathematics that describes space-time curvature inherently requires second-rank tensors, and second-rank tensors in quantum field theory correspond to spin-2 particles. Einstein's geometric theory of gravity and quantum mechanics are connected at the deepest mathematical level. This connection becomes even more remarkable when you understand what makes spin-2 particles so special. Unlike particles with other spins, spin-2 particles must couple universally to all forms of energy and matter. They can't choose to interact with some particles and ignore others. This universal coupling is exactly what we observe with gravity. Gravity affects everything equally, from photons to planets to people. But Einstein realized something even more profound. If spin-2 particles couple universally to everything, including themselves, then they create a self-interacting field that automatically produces the non-linear effects we see in general relativity. The fact that massive objects create stronger gravitational fields, the way gravitational waves carry energy and momentum, the precession of planetary orbits, all of these emerge naturally from the spin-2 nature of gravitons. This is where Einstein's insight becomes truly revolutionary. He understood that the spin-2 property of gravitons means that gravity isn't just another force. Gravity is the manifestation of quantum mechanics operating at the scale of space-time geometry. Every quantum fluctuation in the gravitational field contributes to the overall curvature of spacetime, and every curve in spacetime reflects the quantum mechanical properties of the matter and energy it contains. Now, you might be wondering why this incredible insight remained hidden for so long. The answer lies in the mathematical complexity of working with spin-2 fields. Unlike the relatively simple mathematics of spin-1 electromagnetism, or even spin-1/2 matter particles, spin-2 fields require sophisticated tensor calculus and nonlinear field equations. The mathematics is so complex that it took decades for physicists to fully understand what Einstein had discovered. But the experimental evidence for Einstein's spin-2 insight has been mounting for years. When the LIGO gravitational wave detectors made their first historic detection in 2015, they weren't just confirming Einstein's prediction of gravitational waves. They were providing direct evidence for the spin-2 nature of gravity itself. The gravitational waves detected by LIGO have exactly the polarization patterns predicted for spin-2 particles. Unlike electromagnetic waves, which oscillate in two perpendicular directions, gravitational waves have quadrupole oscillations that stretch and compress space in a characteristic plus and cross pattern. This unique signature is the smoking gun evidence for spin-2 gravitons. Even more remarkably, recent experiments have detected what researchers call chiral graviton modes in laboratory settings. These are collective excitations in certain materials that behave exactly like the gravitons predicted by Einstein's theory. They have spin-2 characteristics and emerge from quantized fluctuations in the material's metric properties. We're literally seeing Einstein's hidden equation manifest in the laboratory. But the most profound implication of Einstein's spin-2 insight comes from string theory. When physicists developed string theory as a potential theory of quantum gravity, they made an astonishing discovery. String theory naturally contains spin-2 particles. In fact, any consistent quantum theory of strings automatically includes gravitons as fundamental excitations of closed strings. This isn't a coincidence. It's a deep mathematical necessity. String theory reveals that spin-2 gravitons are as fundamental to the structure of reality as the strings themselves. The geometry of space-time emerges from the quantum mechanical properties of these strings, exactly as Einstein's hidden equation predicted. What makes this even more extraordinary is that string theory shows how all the fundamental forces of nature arise from different vibrational modes of the same underlying strings. Gravitons correspond to the lowest energy vibrations of closed strings. Higher energy vibrations produce the particles that carry electromagnetic, weak, and strong nuclear forces. Einstein's dream of a unified field theory is realized through the spin-2 connection between quantum mechanics and space-time geometry. The implications extend far beyond theoretical physics. Understanding the spin-2 nature of gravity is opening new windows into the most extreme environments in the universe. When black holes merge, they create ripples in spacetime that carry away enormous amounts of energy in the form of gravitational waves. These waves are literally streams of spin-2 gravitons carrying information about events that would be impossible to observe through any other means. We're entering an era of gravitational wave astronomy where spin-2 particles become our messengers from the most violent and energetic events in the cosmos. Neutron-star collisions, black hole mergers, and potentially even the quantum fluctuations from the Big Bang itself all leave their signatures in the spin-2 gravitons that propagate across billions of light-years to reach our detectors. But perhaps the most mind-bending aspect of Einstein's hidden equation is what it tells us about the nature of reality itself. If gravitons are quantum fluctuations of space-time, then space-time is not the fixed background stage that Newton imagined. Space-time is a dynamic, quantum mechanical entity that responds to and shapes the matter and energy it contains. This means that at the smallest scales, space-time itself must be quantized. Just as electromagnetic fields come in discrete photon packets, the geometry of space-time comes in discrete graviton packets. At the Planck scale, where quantum effects become as strong as gravitational effects, space-time becomes a foaming sea of quantum fluctuations, constantly creating and destroying tiny bubbles of geometry. Einstein's Spin-2 insight reveals that we live in a universe where geometry and quantum mechanics are inseparably intertwined. Every quantum measurement, every particle interaction, every fluctuation in energy density contributes to the overall geometry of spacetime. And every curve in spacetime influences the quantum mechanical behavior of particles and fields. This is the profound truth hidden in Einstein's equations. The universe is not made of matter moving through empty space. The universe is made of quantum information encoded in the geometry of spacetime itself, with spin-2 particles serving as the fundamental carriers of this geometric information. But here's where Einstein's hidden equation becomes truly extraordinary. The mathematical framework he discovered reveals something that should make every physicist's head spin. When we examine the quantum field theory of spin-2 particles, we find that they exhibit a property called gauge invariance. This isn't just technical jargon, it's the key to understanding why gravity behaves so differently from every other force in nature. Gauge invariance means that the physical effects of gravitons don't depend on how we choose to describe them mathematically. Just as you can describe the same location using different coordinate systems without changing where you actually are, gravitons create the same physical effects regardless of how we parameterize the gravitational field. But here's the stunning part. This gauge invariance is what forces gravitons to couple universally to all forms of energy and matter. Think about what this means. Other particles can be choosy about their interactions. Photons interact with electrically charged particles but ignore neutral ones. W and Z bosons only interact with particles that carry weak charge, but gravitons have no choice. The spin-2 gauge invariance demands that they interact with absolutely everything that carries energy or momentum. This universal coupling isn't an accident or a quirk of nature. It's a mathematical necessity built into the deepest structure of space-time itself. Einstein understood that this universal coupling creates a feedback loop unlike anything else in physics. When gravitons interact with matter, they create curvature in space-time, but that curvature contains energy, which means gravitons must interact with their own field. This self-interaction is what makes gravity non-linear and gives rise to phenomena like gravitational waves carrying energy away from accelerating masses. The mathematics becomes even more beautiful when you realize that Einstein's field equations are the unique solution to this self-consistency requirement. If you start with the assumption that massless spin-2 particles exist and must be gauge invariant, you inevitably arrive at Einstein's theory of general relativity. The geometric description of gravity isn't just one possible theory among many. It's the only mathematically consistent way to describe how spin-2 particles behave. But Einstein's insight goes deeper still. He recognized that the spin-2 nature of gravitons creates a direct link between quantum mechanics and the causal structure of spacetime. In quantum field theory, the spin of a particle determines how its wave function transforms under rotations. Spin-2 particles have wave functions that transform like second-rank tensors, which are precisely the mathematical objects that describe the metric of spacetime. This connection is so fundamental that it reveals why spacetime must have 4 dimensions. The mathematics of spin-2 particles in 4-dimensional spacetime produces exactly 2 independent polarization states for gravitational waves. These correspond to the plus and cross polarizations that LIGO detects when black holes merge. In any other number of dimensions, the mathematics either becomes inconsistent or produces the wrong number of polarization states. Here's where the story takes an unexpected turn. When physicists tried to build a complete quantum theory of gravity using spin-2 particles, they encountered a seemingly insurmountable problem. The theory appeared to be non-renormalizable, meaning that quantum corrections produced infinite results that couldn't be absorbed into the basic parameters of the theory. For decades, this suggested that quantum gravity might be fundamentally impossible, but Einstein's hidden equation contains the solution to this puzzle. The key insight is that gravity isn't just another quantum field theory. It's an effective field theory that emerges from something more fundamental. At low energies, where the quantum corrections are small, Einstein's equations provide an excellent approximation, but at high energies approaching the Planck scale, new physics must emerge to tame the quantum infinities. This is where string theory enters the picture in the most elegant way possible. String theory doesn't just contain spin-2 particles, it demands them. When you write down the equations describing the quantum mechanics of vibrating strings, gravitons emerge automatically as the lowest energy excitation modes of closed strings. You don't put gravity into string theory. Gravity comes out of string theory whether you want it or not. The mathematical beauty of this emergence is breathtaking. In string theory, the problems that plagued earlier attempts at quantum gravity simply disappear. The infinite quantum corrections that seem to make quantum gravity impossible are automatically regulated by the finite size of strings. The theory is UV complete, meaning it remains mathematically consistent even at arbitrarily high energies. But string theory reveals something even more profound about Einstein's spin-2 insight. The theory shows that space-time geometry isn't fundamental. Instead, space-time emerges from the quantum entanglement patterns between different regions of the string theory vacuum. The metric of space-time, which describes distances and angles, is actually a measure of how strongly different parts of the quantum system are entangled with each other. This emergence of geometry from entanglement represents the ultimate validation of Einstein's hidden equation. The spin-2 particles that we interpret as gravitons are really collective excitations of a vast network of quantum entanglement that spans the entire universe. When we measure gravitational waves or detect the effects of curved spacetime, we're actually probing the entanglement structure of quantum reality itself. The implications are staggering. Black holes, which appear to be regions of infinite curvature in Einstein's classical theory, are actually finite temperature quantum systems with well-defined entropy. The information paradox that has puzzled physicists for decades dissolves when you realize that black holes are entangled quantum systems whose information content is encoded in the subtle correlations between spin-2 modes at their boundaries. Even more remarkably, the holographic principle that emerges from string theory shows that all the information in any region of spacetime can be encoded on its boundary. This isn't just a mathematical curiosity, it's a fundamental property of how spin-2 particles organize quantum information. The three-dimensional volume of space that we experience is actually a holographic projection of information stored on a two-dimensional surface. Einstein's hidden equation reveals that we live in a holographic universe where the apparent three-dimensional reality emerges from quantum information processing on distant boundaries. Every graviton that propagates through spacetime carries holographic information about the quantum state of matter and energy throughout the universe. Gravity isn't just a force that warps spacetime, it's the mechanism by which quantum information is distributed and processed on cosmic scales. This holographic nature of gravity explains why Einstein's theory has such remarkable predictive power. When LIGO detected gravitational waves from merging black holes billions of light-years away, the detected waveforms matched Einstein's predictions to extraordinary precision. This wasn't just a triumph of classical physics, it was confirmation that the holographic encoding of quantum information in Spin-2 gravitons preserves correlations across vast distances and timescales. The recent detection of chiral graviton modes in laboratory materials provides even more direct evidence for Einstein's Spin-2 insight. These experiments show that when certain quantum materials are subjected to strain or deformation, they develop collective excitations with exactly the properties predicted for gravitons. The materials effectively simulate curved spacetime, and the excitations behave like quantized geometric fluctuations. These laboratory gravitons exhibit the characteristic spin-2 polarization patterns and couple to external fields in precisely the way Einstein's theory predicts. Even more remarkably, they demonstrate the gauge invariance that makes gravitons special among all the particles in nature. The experiments provide a direct window into the quantum mechanics of curved spacetime without requiring the extreme energies of black hole mergers or cosmic inflation. But perhaps the most profound validation of Einstein's hidden equation comes from cosmology. The cosmic microwave background radiation that fills the universe carries the imprint of quantum fluctuations from the earliest moments after the Big Bang. These fluctuations, amplified by cosmic inflation, created the seeds that grew into galaxies and large-scale structure. The polarization patterns in the cosmic microwave background provide direct evidence for primordial gravitational waves generated during inflation. These waves carry the signatures of spin-2 quantum fluctuations from a time when the universe was smaller than a proton. The detection of B-mode polarization would represent the ultimate confirmation that spacetime geometry itself has quantum mechanical origins. Einstein's Spin-2 insight predicts that these primordial gravitational waves should have left their mark on the cosmic microwave background through a characteristic pattern of polarization. The waves stretch and squeeze the geometry of spacetime, creating correlations in the temperature and polarization of the background radiation that can only be explained by quantum gravitational effects. Current experiments are pushing toward the sensitivity needed to detect these primordial gravitational waves. When they succeed, we'll have direct observational evidence that the geometry of spacetime underwent quantum fluctuations during the inflationary epoch. This will complete the circle from Einstein's theoretical insight to experimental confirmation that spin-2 particles are indeed the fundamental carriers of gravitational interaction. The mathematical elegance of Einstein's hidden equation extends even to the most speculative frontiers of theoretical physics. In theories of extra dimensions, spin-2 gravitons can propagate through the full higher dimensional space, while other particles remain confined to lower dimensional surfaces. This could explain why gravity appears so much weaker than other forces. The gravitons might be diluted by spreading into extra dimensions that we can't directly perceive. Advanced theories like ADS/CFT correspondence show that Einstein's spin-2 insight connects to the deepest structures in theoretical physics. The correspondence relates gravitational theories in higher dimensional curved spacetime to quantum field theories without gravity in lower dimensional flat spacetime. The spin-2 gravitons in the higher dimensional theory correspond to stress-energy fluctuations in the lower dimensional theory. This remarkable duality suggests that Einstein's geometric description of gravity might be just one way of describing quantum mechanical phenomena that can be equally well understood without any reference to curved spacetime at all. The spin-2 particles that create spacetime curvature in one description become emergent collective modes in an alternative quantum field theory description. Einstein's hidden equation reveals that the boundary between quantum mechanics and gravity dissolves when viewed from the proper mathematical perspective. Spin-2 particles don't just connect quantum physics to spacetime, they show us that this distinction is itself an artifact of our limited perspective on the underlying quantum information processing that constitutes physical reality. As we stand on the brink of a new era in gravitational physics, with space-based detectors preparing to observe gravitational waves across the electromagnetic spectrum and quantum experiments probing the foundations of spacetime, Einstein's Spin-2 insight continues to guide our understanding. The hidden equation he discovered over a century ago remains our best roadmap for navigating the quantum landscape of gravity and spacetime. The mathematical beauty deepens when we examine how Einstein's Spin-2 framework predicts the behavior of matter under extreme gravitational conditions. Near the event horizons of black holes, where spacetime curvature reaches its most dramatic extremes, the Spin-2 nature of gravitons creates effects that classical physics cannot explain but quantum mechanics demands. Consider what happens when matter falls toward a black hole. As it accelerates through increasingly curved spacetime, it radiates gravitational waves that carry away energy and angular momentum. But these aren't just classical waves rippling through a fixed background. They're streams of Spin-2 gravitons that encode quantum information about the infalling matter's internal structure. Einstein's hidden equation reveals that this process creates what physicists now call the black hole information paradox. When matter crosses the event horizon, its quantum information seems to disappear from the observable universe. Classical general relativity suggests this information is lost forever, violating one of the most fundamental principles of quantum mechanics. But the Spin-2 nature of gravitons provides a resolution that Einstein himself could never have imagined. The key insight emerges from understanding how Spin-2 particles interact with quantum entanglement. When gravitons carry information away from a black hole through Hawking radiation, they don't just transport energy, they maintain quantum correlations with the matter that originally fell into the black hole. These correlations are encoded in the subtle phase relationships between different Spin-2 modes, creating a quantum mechanical bridge between the interior and exterior of the black hole. This bridge operates through a mechanism that Einstein's equations predict, but that requires quantum mechanics to fully understand. The Spin-2 gravitons that make up the black hole's geometry are entangled with the gravitons in the surrounding spacetime. This entanglement network preserves information about the black hole's formation history and internal structure, even though that information cannot be directly observed from outside the event horizon. Recent theoretical breakthroughs have shown that this entanglement structure gives black holes a holographic nature that emerges directly from Einstein's Spin-2 framework. The information content of everything that ever fell into a black hole remains encoded on its two-dimensional surface, stored in the correlations between Spin-2 graviton modes. The three-dimensional interior that we visualize as curved spacetime is actually a holographic projection of this two-dimensional quantum information. This holographic property isn't limited to black holes. Einstein's Spin-2 insight reveals that all of spacetime has this character. Every region of space can have its information content fully encoded on its boundary through the correlations between graviton modes. This discovery has revolutionized our understanding of what information really means in a quantum gravitational context. The experimental implications are profound. When LIGO detects gravitational waves from merging black holes, it's not just measuring ripples in spacetime, it's decoding holographic information about the quantum states of matter that existed billions of years ago and billions of light years away. Each detected graviton carries quantum correlations that connect us to events across the observable universe. But Einstein's framework predicts even more exotic phenomena. In regions where spacetime curvature approaches the Planck scale, the distinction between gravitons and the geometry they create begins to break down. Spacetime itself becomes subject to quantum uncertainty, fluctuating between different geometric configurations. In physics cannot describe ways that classical. These geometry quantum fluctuations create what physicists call spacetime foam. At distances smaller than the Planck length, spacetime resembles a boiling sea of virtual gravitons constantly appearing and disappearing. These fluctuations are so violent that the very concepts of distance and time lose their classical meaning, yet Einstein's Spin-2 framework provides the mathematical tools needed to describe this quantum geometric chaos. The foam structure emerges naturally from the gauge invariance properties of Spin-2 fields. Just as electromagnetic gauge invariance leads to virtual photon fluctuations in the quantum vacuum, gravitational gauge invariance produces virtual graviton fluctuations that manifest as quantum geometry. These fluctuations carry no net energy or momentum, but they profoundly affect the propagation of matter and radiation through spacetime. Particles traveling through this quantum foam experience tiny random deflections as they interact with virtual gravitons. These deflections are far too small to detect with current technology, but they represent a fundamental limit on the precision with which we can measure distances and time intervals. Einstein's hidden equation predicts that space and time are ultimately granular rather than continuous, with the grain size determined by the Planck scale. This granularity has remarkable consequences for our understanding of causality. In classical relativity, events are connected by well-defined light cones that determine which events can influence each other. But quantum gravitational effects allow for tiny violations of these causal relationships through virtual graviton exchanges. These violations don't permit faster-than-light signaling, but they do create subtle quantum correlations that extend beyond the classical light cone. The implications extend to cosmology in ways that Einstein could never have anticipated. During the inflationary epoch that followed the Big Bang, quantum fluctuations in the gravitational field were stretched to cosmic scales by the exponential expansion of space-time. These stretched fluctuations became the seeds for all the large-scale structure we observe in the universe today. But the spin-2 nature of these fluctuations creates distinctive signatures that differ from what scalar or vector field fluctuations would produce. Gravitational waves from inflation generate a characteristic pattern of polarization in the cosmic microwave background radiation. This pattern, known as B-mode polarization, provides a direct window into quantum gravity operating during the universe's first moments. Current experiments are racing to detect this primordial gravitational wave signature. When they succeed, we'll have observational evidence that space-time geometry underwent quantum fluctuations when the universe was smaller than an atom. This will represent the ultimate validation of Einstein's insight that gravity and quantum mechanics are fundamentally connected through spin-2 particles. The detection challenges are immense because these primordial signals are incredibly weak, but Einstein's framework predicts exactly what to look for. The B-mode polarization should have a characteristic frequency spectrum that reflects the quantum mechanical properties of spin-2 gravitons during inflation. Different models of quantum gravity make different predictions for this spectrum, providing a way to test competing theories about the nature of spacetime at the Planck scale. Meanwhile, advances in gravitational wave astronomy continue to reveal new aspects of Einstein's spin-2 insight. The third-generation detectors now under development will be sensitive enough to observe gravitational waves from the formation of the first black holes in the universe. These observations will provide direct information about how spacetime behaved when the universe was very young and matter densities were extreme. Even more remarkably, space-based gravitational wave detectors will open entirely new frequency ranges for observation. These instruments will be sensitive to gravitational waves with periods ranging from minutes to hours, allowing them to detect massive black hole mergers throughout cosmic history. The accumulated data will create a comprehensive map of how space-time geometry has evolved since the Big Bang. Each detected gravitational wave event provides information about the quantum state of spacetime at the moment of emission. The phase relationships between different polarization modes carry quantum information that has been preserved across billions of years of cosmic expansion. Einstein's spin-2 framework allows us to decode this information and reconstruct the quantum gravitational environment that existed when the waves were generated. This capability transforms gravitational wave astronomy into a form of quantum archaeology. By analyzing the correlations between spin-2 graviton modes in detected signals, researchers can infer properties of matter and spacetime that existed under conditions impossible to recreate in terrestrial laboratories. We're literally observing the quantum mechanics of gravity operating in the most extreme environments the universe has to offer. The technological applications of Einstein's spin-2 insight are only beginning to emerge. Understanding how gravitons interact with matter at the quantum level could lead to new forms of precision measurement that exploit gravitational effects. These techniques might enable detection of dark matter through its gravitational interactions or provide new ways to probe the quantum structure of spacetime directly. More speculatively, mastering the quantum mechanics of spin-2 particles could eventually lead to technologies that manipulate spacetime geometry itself. While such capabilities remain far beyond current technology, Einstein's framework provides the theoretical foundation for understanding how quantum gravitational effects might be amplified or controlled. The mathematical structure underlying these possibilities emerges from the unique properties of spin-2 gauge invariance. Unlike other gauge theories, where the gauge transformations act on internal symmetries, gravitational gauge transformations act on the spacetime coordinates themselves. This creates a direct link between quantum mechanical symmetries and the geometric structure of reality. This coordinate gauge invariance is what allows gravitons to carry information about the global structure of spacetime. Each graviton mode corresponds to a particular way that spacetime can be deformed while preserving its causal structure. The quantum superpositions of these modes create spacetime states that exist in coherent superpositions of different geometric configurations. Such quantum geometric superposition states might seem abstract, but they have measurable consequences. Precision tests of general relativity in strong gravitational fields are beginning to probe regimes where these quantum gravitational effects could become detectable. Future experiments with ultra-precise atomic clocks or matter wave interferometers might be sensitive enough to observe the quantum fluctuations of spacetime geometry directly. The philosophical implications of Einstein's spin-2 framework extend far beyond physics. If spacetime geometry is fundamentally quantum mechanical, then the classical notion of an objective, observer-independent reality becomes questionable. The geometry of spacetime depends on how we choose to measure it, with different measurement procedures potentially yielding different results. This measurement-dependent nature of spacetime geometry doesn't lead to relativism or subjectivity in physics. Instead, it reveals that reality has a quantum informational structure that transcends the classical distinction between observer and observed. The spin-2 gravitons that constitute spacetime geometry are carriers of quantum information that connects all parts of the universe through non-local correlations. These correlations operate through the entanglement networks that Einstein's framework reveals to be fundamental to spacetime structure. When gravitons become entangled through their mutual interactions, they create quantum correlations that persist even when the particles are separated by vast distances. These correlations don't violate relativistic causality, but they do create subtle connections between distant regions of spacetime. The strength of these quantum gravitational correlations depends on the history of interactions between different regions of spacetime. Areas that were in causal contact during cosmic inflation remain quantum mechanically connected through graviton entanglement, even though they're now larger than the observable separated by distances universe. This creates a hidden web of quantum correlations that spans the entire cosmos. Understanding this cosmic entanglement network could provide new insights into fundamental questions about the nature of time and causality. If the quantum correlations between gravitons create connections that transcend classical spacetime relationships, then the flow of time itself might emerge from the dynamics of quantum information processing in the gravitational field. Einstein's spin-2 insight suggests that time isn't a fundamental aspect of reality, but rather an emergent property of how quantum information is distributed and processed through graviton interactions. The arrow of time that we experience might reflect the way quantum entanglement spreads through the gravitational field as the universe evolves. This emergent view of time has profound implications for our understanding of consciousness and the nature of physical law. If time emerges from quantum gravitational processes, then the subjective experience of temporal flow might be intimately connected to the way our brains process quantum information. The spin-2 particles that constitute spacetime might be the fundamental carriers of the information processing that creates conscious experience. Such connections between quantum gravity and consciousness remain highly speculative, but they illustrate the far-reaching implications of Einstein's hidden equation. By revealing the quantum informational nature of space-time geometry, the Spin-2 framework opens new avenues for understanding the relationship between mind and matter, between information and reality, between the quantum and classical worlds. As we continue to explore these connections, Einstein's century-old insight continues to guide our understanding. The spin-2 particles that he recognized as fundamental to gravitational physics have revealed themselves to be the carriers of quantum information that constitute the very fabric of reality. His hidden equation remains our best roadmap for navigating the quantum landscape where geometry, information, and consciousness converge. The experimental verification of Einstein's spin-2 predictions continues to accelerate as new technologies push the boundaries of measurement precision. Underground detectors are being developed to search for the quantum fluctuations of space-time that should be constantly occurring around us. These instruments use laser interferometry to measure distance variations smaller than the classical limit imposed by the uncertainty principle. Such measurements probe the quantum nature of space-time geometry itself. If Einstein's framework is correct, then even in the absence of gravitational waves from distant sources, local spacetime should exhibit quantum fluctuations driven by the zero-point motion of graviton modes. These fluctuations represent the quantum mechanical ground state of spacetime geometry, analogous to the zero-point energy of electromagnetic fields. The detection of these quantum gravitational fluctuations would provide direct evidence that space-time geometry is subject to quantum mechanical uncertainty. This would represent the ultimate confirmation of Einstein's insight that gravity and quantum mechanics are unified through the spin-2 nature of space-time itself. We would finally have experimental proof that we live in a quantum gravitational universe. The quest to detect these quantum space-time fluctuations has led physicists to develop instruments of unprecedented sensitivity. Deep underground laboratories shield detectors from seismic noise and cosmic radiation, creating environments quiet enough to potentially observe the quantum jitter of geometry itself. These facilities represent humanity's attempt to eavesdrop on conversations between gravitons that have been whispering in the quantum vacuum since the universe began. But Einstein's spin-2 framework predicts something even more extraordinary about these quantum fluctuations. Unlike other quantum fields where fluctuations remain localized, gravitational quantum fluctuations can create correlations that extend across macroscopic distances. This happens because space-time itself is the medium through which these correlations propagate. When one region of space undergoes a quantum fluctuation, it can instantaneously affect the geometric properties of distant regions through graviton entanglement. Think about what this means for the nature of locality in physics. In classical relativity, events at different locations are independent unless connected by signals traveling at the speed of light. But Einstein's quantum gravitational framework reveals that spacetime geometry creates hidden channels of correlation that bypass these classical limitations. Not through faster-than-light signaling, but through quantum entanglement that was established when different regions of space were in causal contact during the universe's early moments. These quantum geometric correlations become most apparent in systems where gravitational effects dominate over other forces. Near black holes, where spacetime curvature reaches extreme values, the quantum fluctuations of geometry create phenomena that have no analogue in flat spacetime physics. The event horizon itself becomes a quantum mechanical boundary where information processing occurs through graviton interactions. Recent theoretical work has shown that black hole event horizons behave like quantum error-correcting codes. The spin-2 gravitons that constitute the horizon's geometry can detect and correct errors in the quantum information falling into the black hole. This error correction mechanism prevents information from being truly lost, instead encoding it in the subtle correlations between graviton modes that extend throughout the black hole's exterior geometry. This discovery resolves the information paradox through a mechanism that Einstein could never have anticipated. The spin-2 nature of gravitons creates a natural quantum computing architecture within black hole spacetime. Information doesn't disappear when it crosses the event horizon. Instead, it gets processed by the gravitational field's quantum computational structure and eventually returned to the external universe through Hawking radiation. The implications extend far beyond black hole physics. If space-time geometry naturally implements quantum error correction, then the universe itself might be a vast quantum computer processing information through graviton interactions. Every quantum measurement, every particle interaction, every fluctuation in energy density contributes to this cosmic computation. Einstein's hidden equation reveals that physical reality might be fundamentally computational, with spin-2 particles serving as the universe's processing elements. This computational view of spacetime helps explain why the laws of physics have the mathematical structure they do. Physical laws aren't arbitrary rules imposed on reality from outside. They're algorithms that emerge from the information processing capabilities of quantum gravitational systems. The elegance and mathematical beauty of Einstein's equations reflect the computational efficiency of spin-2 quantum error correction. But the story becomes even more remarkable when we consider how this quantum computational structure evolves over cosmic time. As the universe expands and cools, the gravitational field's computational capacity changes. During the early universe's hot dense phase, quantum gravitational effects dominated and the cosmic computation proceeded at maximum efficiency. As expansion continued and matter became more dilute, classical spacetime geometry emerged as an approximation to the underlying quantum computation. We're currently living through a transitional epoch where quantum gravitational effects are generally weak but still detectable under extreme conditions. The merging black holes that LIGO observes represent moments when the universe's quantum computational architecture becomes temporarily visible through classical instruments. Each detected gravitational wave carries information about quantum processes that normally remain hidden beneath the smooth geometry of classical spacetime. Future observations will probe deeper into this quantum computational structure. Space-based gravitational wave detectors will observe mergers between supermassive black holes, events that involve quantum information processing on scales comparable to entire galaxies. These observations will reveal how quantum gravitational computation operates in the most extreme environments the universe can create. Even more exciting are prospects for observing the universe's quantum computational activity directly. Theoretical proposals suggest that cosmic strings, if they exist, would create gravitational wave signatures that reveal the quantum structure of spacetime during phase transitions in the early universe. These strings would be one-dimensional defects in the gravitational field's quantum computational fabric, creating detectable patterns in the gravitational wave background. The search for cosmic strings represents more than just another observational target. These objects would provide direct evidence that spacetime underwent quantum phase transitions during its early evolution. Just as water undergoes phase transitions between ice, liquid, and vapor, spacetime might have between different quantum computational phases undergone transitions as the universe cooled from its initial state. Einstein's Spin-2 framework predicts that these phase transitions would leave permanent signatures in the universe's large-scale structure. The quantum computational algorithms that govern graviton interactions would have changed discontinuously at transition points, creating observable effects in the distribution of matter and energy throughout the cosmos. Current surveys of galaxy distributions and cosmic microwave background patterns are beginning to probe these signatures. The statistical properties of large-scale structure carry information about the quantum gravitational processes that operated during the universe's first moments. By analyzing these patterns, cosmologists can reconstruct the history of spacetime's quantum computational evolution. This reconstruction reveals something profound about the relationship between information and energy in gravitational systems. Einstein's equations show that matter and energy determine space-time curvature, but the quantum gravitational perspective reveals that information plays an equally fundamental role. The quantum information content of gravitational fields determines their computational capabilities, which in turn influence how matter and energy behave. This creates a feedback loop between information, computation, and gravity that operates on all scales from quantum to cosmic. Local quantum gravitational computations influence the global structure of spacetime, while the global geometry affects local quantum processes. The universe becomes a self-modifying quantum computer where the hardware and software evolve together through gravitational interactions. Understanding this feedback loop requires mathematical tools that go far beyond Einstein's original equations. Modern quantum field theory, string theory, and quantum information theory all contribute essential insights. But the conceptual foundation remains Einstein's recognition that spin-2 particles create a unique connection between quantum mechanics and spacetime geometry. The mathematical elegance of this connection becomes most apparent in the holographic principle that emerges from string theory. This principle shows that any region of spacetime can have its information content fully encoded on its boundary through correlations between graviton modes. The three-dimensional volume that appears to contain matter and energy is actually a holographic projection of information stored in two-dimensional surface modes. This holographic structure isn't just a theoretical curiosity, it has practical implications for how we understand and predict gravitational phenomena. When LIGO detects gravitational waves, it's essentially reading holographic information that was encoded on the surfaces of merging black holes billions of years ago. The detected waveforms carry complete information about the quantum states of matter that existed under conditions impossible to recreate in terrestrial laboratories. The holographic principle also explains why gravitational physics exhibits such remarkable universality. Despite the enormous differences between merging stellar mass black holes and colliding galaxies, the underlying gravitational dynamics follow the same mathematical patterns. This universality reflects the holographic encoding of information in gravitations, which on coral create scale-invariant structures that appear similar across vast ranges of mass and energy. But perhaps the most profound implication of Einstein's spin-2 insight concerns the nature of measurement and observation in quantum gravitational systems. In ordinary quantum mechanics, measurement devices are treated as classical systems that aren't affected by the quantum uncertainty of the systems they observe. But in quantum gravity, the measuring apparatus and the measured system are both described by quantum gravitational fields. This creates a new kind of measurement problem, where the observer and observed are both subject to quantum gravitational uncertainty. The spin-2 nature of gravitons means that every measurement process involves quantum fluctuations of spacetime geometry. These fluctuations can create correlations between measurement outcomes that have no analogue in non-gravitational quantum mechanics. Recent theoretical work has shown that these gravitational measurement correlations could provide new ways to test quantum mechanics itself. If Einstein's framework is correct, then precision measurements of gravitational effects should exhibit quantum correlations that violate classical expectations in ways that go beyond ordinary quantum mechanical violations of local realism. Such experiments would probe the deepest foundations of physical reality. They would test whether the quantum mechanical description of nature remains valid when gravity is included as a quantum field rather than a classical background. The results could reveal new principles of physics that transcend both quantum mechanics and general relativity. The experimental challenges are formidable because gravitational effects are so weak compared to other forces. But advances in atomic physics and quantum optics are creating new possibilities for ultra-precise measurements. Atomic clocks can now detect gravitational time dilation effects over distances of centimeters. Matter wave interferometers can measure gravitational accelerations with precisions approaching the quantum limit. These technologies are approaching the sensitivity needed to observe quantum gravitational effects directly. Future experiments might detect the quantum fluctuations of spacetime geometry or measure the gravitational entanglement between separated masses. Such observations would provide direct evidence for Einstein's insight that spacetime itself is a quantum mechanical system. The implications would extend far beyond fundamental physics. Understanding how to control and manipulate quantum gravitational effects could lead to revolutionary technologies. While such applications remain highly speculative, Einstein's framework provides the theoretical foundation for exploring possibilities that seemed like science fiction just decades ago. More immediately, the Spin-2 insight is driving advances in gravitational wave astronomy and precision measurement. Each new detection provides more detailed information about the quantum structure of spacetime under extreme conditions. The accumulated data is creating an increasingly complete picture of how quantum mechanics and gravity unite through the elegant mathematics of spin-2 particles. As we stand on the threshold of detecting quantum gravitational effects directly, Einstein's hidden equation continues to guide our understanding. The mathematical framework he discovered over a century ago remains our best roadmap for navigating the quantum gravitational landscape where information, computation, and geometry converge to create the reality we experience. The journey from Einstein's initial insight about quantized gravitational radiation to today's sophisticated understanding of quantum spacetime represents one of the greatest intellectual achievements in human history. Yet we're still only beginning to explore the implications of his discovery. The spin-2 particles that connect quantum physics to spacetime hold secrets that will likely take centuries to fully understand. But with each new gravitational wave detection, each advance in quantum measurement technology, each theoretical breakthrough in our understanding of quantum geometry, we come closer to grasping the full significance of Einstein's hidden equation. We're living through a golden age of discovery where the deepest mysteries of space, time, and quantum reality are finally beginning to reveal their secrets. The universe that emerges from this understanding is far stranger and more wonderful than anything Einstein himself could have imagined. It's a universe where space-time is alive with quantum activity, where information and geometry dance together in cosmic computation, where consciousness and cosmos might be intimately connected through the quantum mechanical processing of gravitational information. Einstein's spin-2 insight has opened a window into this quantum gravitational reality. As we continue to peer through that window, we're discovering that the boundary between physics and philosophy, between matter and mind, between the quantum and classical worlds, is far more fluid than we ever suspected. The hidden equation that connects spin-2 particles to spacetime geometry is revealing itself to be nothing less than a user's manual for understanding the deepest nature of existence itself. The mathematical poetry of Einstein's spin-2 framework becomes even more profound when we examine how it predicts the behavior of spacetime at the quantum scale. Imagine trying to measure the position of a single graviton with perfect accuracy. Einstein's equations reveal something that should shake you to your core. The very act of measurement creates such violent fluctuations in space-time geometry that the concepts of position and momentum lose all meaning. This isn't just theoretical speculation. The mathematics demands it. When you try to localize a graviton to a region smaller than the Planck length, the energy required for such precision becomes so enormous that it creates a black hole larger than the region you're trying to measure. The universe literally prevents you from probing space-time geometry below a fundamental scale. But here's where Einstein's insight becomes truly revolutionary. These measurement limitations aren't bugs in the theory, they're features. The spin-2 nature of gravitons creates a natural cutoff that prevents the mathematical infinities that plague other attempts at quantum gravity. Reality protects itself from paradox through the elegant mathematics of quantum geometry. This self-protection mechanism operates through what physicists call the holographic bound. Any region of spacetime can contain only a finite amount of information, determined by the area of its boundary rather than its volume. This bound emerges directly from the spin-2 properties of gravitons, which can only encode information in specific geometric patterns. Think about what this means for the nature of reality itself. We live in a universe where information has geometric properties and geometry has informational content. Every graviton carries quantum bits of data about the state of spacetime, and every bit of quantum information contributes to the curvature of geometry. The universe is simultaneously a geometric structure and an information processing system. The experimental evidence for this information-geometry duality continues to mount. When physicists analyze the entropy of black holes, they find exactly the relationship Einstein's spin-2 framework predicts. The entropy scales with the area of the event horizon, not its volume, confirming that gravitational information is encoded on surfaces rather than throughout space. But black holes aren't the only systems that exhibit this holographic behavior. Recent experiments with strongly correlated quantum materials have revealed similar patterns. When these materials undergo phase transitions, they develop collective excitations with spin-2 properties that encode information about the entire system's quantum state on its boundaries. These laboratory demonstrations of holographic physics provide direct access to phenomena that would otherwise require black hole-scale energies to observe. Researchers can study how quantum information gets processed by spin-2 fields using tabletop experiments that probe the fundamental nature of spacetime itself. The results are reshaping our understanding of how quantum mechanics and gravity interface. The spin-2 particles that Einstein identified as carriers of gravitational interaction turn out to be the fundamental units of cosmic information processing. Every gravitational wave carries quantum data about events that occurred billions of years ago and billions of miles away. When LIGO detected its first gravitational waves, it wasn't just confirming Einstein's prediction about ripples in spacetime, it was demonstrating humanity's ability to decode quantum information that had been preserved in the geometric structure of the universe since black holes first began merging in the cosmic dark ages. The information content of these signals reveals details about the quantum states of matter under conditions that dwarf anything achievable in terrestrial laboratories. The merging black holes that created the detected waves processed quantum information at rates that exceed all the computers humanity has ever built, combined and multiplied by trillions. This cosmic computation operated through the spin-2 gravitons that constitute the black hole's event horizons. As the holes spiraled together, their quantum gravitational fields performed calculations that determined how energy and angular momentum would be distributed in the final merger product. The gravitational waves carry the output of these calculations encoded in their amplitude and phase relationships. Understanding this cosmic computation has profound implications for how we think about the relationship between physics and mathematics. The laws of nature aren't just mathematical descriptions of physical processes, they're computational algorithms that the universe executes through quantum gravitational interactions. Reality computes itself into existence through the processing power of spin-2 particles. This computational view of physics helps explain why mathematics is so unreasonably effective at describing natural phenomena. Mathematical structures don't just model reality. They are reality, at least at the level of information processing that constitutes the foundation of physical existence. Einstein's spin-2 insight reveals that the universe is mathematical, not because we describe it with mathematics, but because mathematical processing is what creates the phenomena we observe. The implications extend to the deepest questions about the nature of time and causality. If physical processes are computational operations performed by gravitational fields, then the flow of time might reflect the sequential execution of these cosmic of time cool algorithms. The arrow'd be a consequence of how quantum information flows through the spin-2 graviton networks that constitute spacetime geometry. Recent theoretical work suggests that this computational perspective might resolve long-standing paradoxes about the nature of time travel and causal loops. If spacetime is a quantum computational system, then closed time-like curves might represent feedback loops in the cosmic calculation rather than genuine violations of causality. The universe's computational architecture might naturally prevent paradoxes by implementing error correction protocols that maintain logical consistency. These error correction mechanisms would operate through the gauge invariance properties that make spin-2 gravitons unique among all particles. Just as quantum error correction codes can protect information from decoherence, gravitational gauge invariance might protect the universe from logical inconsistencies that would arise from causal violations. The mathematical structure of these protection mechanisms reveals deep connections between quantum information theory and gravitational physics. The same mathematical tools that describe quantum error correction in laboratory systems apply to the cosmic information processing that occurs through gravitational interactions. Einstein's equations emerge as the macroscopic manifestation of quantum error correction operating on cosmic scales. But perhaps the most remarkable prediction of Einstein's Spin-2 framework concerns the ultimate fate of information in our expanding universe. As cosmic expansion continues and the universe becomes increasingly dilute, the gravitational field's computational capacity will gradually decline. Eventually, thermal fluctuations will overwhelm the quantum correlations that maintain information coherence. This process will unfold over timescales that dwarf the current age of the universe by factors of trillions. But Einstein's equations predict that even the longest-lived black holes will eventually evaporate through Hawking radiation, returning their stored information to the cosmic quantum field. The universe will end not with a bang or a whimper, but with the completion of a cosmic computation that began with the Big Bang. The final output of this computation will be a maximally entropic state where all possible quantum information has been processed and all possible correlations have been explored. But even in this heat-death scenario, the spin-2 structure of spacetime ensures that the universe retains its capacity for quantum fluctuations, potentially cations that could new cycles of cosmic evolution. This cyclical vision of cosmic history emerges naturally from Einstein's framework when extended to the quantum gravitational regime. The spin-2 particles that create spacetime geometry also provide the mechanism for its eventual renewal. Quantum fluctuations in the vacuum state can grow into macroscopic spacetime regions through the same inflationary processes that created our current universe. If this picture is correct, then we're living in just one phase of an eternal cosmic computation that cycles through periods of expansion, evolution, heat death, and rebirth. Each cycle explores different possibilities for how quantum information can be organized and processed through gravitational interactions. The universe becomes an eternal explorer of its own mathematical potential. The evidence for this eternal cycling remains highly speculative, but Einstein's Spin-2 framework provides the mathematical tools needed to make testable predictions. Future observations of the cosmic microwave background might reveal signatures of quantum fluctuations that predate the Big Bang, indicating that our universe emerged from the quantum vacuum left by a previous cosmic cycle. Even more remarkably, the holographic principle suggests that information from previous cosmic cycles might be encoded in the structure of spacetime itself. The quantum correlations between spin-2 graviton modes could preserve data about earlier universes, creating an eternal archive of cosmic history embedded in the fabric of reality. Accessing this archive would require mastering the quantum mechanics of spacetime to a degree far beyond current capabilities, but Einstein's framework suggests that such mastery is theoretically possible. The same spin-2 particles that create spacetime geometry could potentially be manipulated to decode the information they carry about the universe's deep history. The technological implications remain far in the future, but the conceptual framework is already transforming how physicists think about the relationship between information, computation, and physical reality. Einstein's hidden equation reveals that these aren't separate aspects of nature, but different perspectives on the same underlying quantum gravitational processes. As our experimental capabilities continue to advance, we're gaining direct access to these processes for the first time in human history. Gravitational wave detectors are reading quantum information from black hole mergers. Quantum sensors are approaching the precision needed to observe spacetime fluctuations directly. Laboratory experiments are creating artificial spacetimes where spin-2 physics can be studied under controlled conditions. Each advance brings us closer to the ultimate goal of understanding how consciousness itself might emerge from the quantum computational processes that constitute physical reality. If Einstein's insight is correct, then the spin-2 particles that create spacetime geometry might also be the carriers of the information processing that creates conscious experience. This possibility connects Einstein's mathematical framework to questions about the nature of mind and meaning that extend far beyond physics. The same quantum gravitational processes that determine the evolution of galaxies and the merger of black holes might also determine the emergence of awareness and understanding in complex systems like biological brains. The mathematics suggests profound connections between the computational capacity of gravitational fields and the information processing capabilities required for consciousness. Both involve the integration of quantum information across multiple scales and the creation of coherent patterns from seemingly random fluctuations. If these connections are real, then consciousness might not be limited to biological systems. Any sufficiently complex arrangement of quantum gravitational fields could potentially develop awareness through the natural information processing capabilities of spin-2 particles. The universe itself might be conscious in ways we're only beginning to imagine. These speculative possibilities illustrate the far-reaching implications of Einstein's discovery. By revealing the quantum computational nature of space-time, the Spin-2 framework opens new avenues for understanding the deepest mysteries of existence. From the origin of the universe to the nature of consciousness, from the flow of time to the meaning of information, Einstein's hidden equation provides a mathematical foundation for exploring questions that touch the very core of what it means to exist. As we continue to develop the experimental and theoretical tools needed to fully exploit Einstein's insight, we're embarking on a journey of discovery that will likely transform human understanding as profoundly as the original development of quantum mechanics and relativity. The spin-2 particles that connect quantum physics to spacetime are guiding us toward a new synthesis that could revolutionize not just physics, but our entire worldview. The mathematical elegance of this emerging synthesis reflects the deep unity that Einstein always believed must exist at the foundation of natural law. His search for a unified field theory led him to insights about spin-2 particles that we're only now beginning to fully appreciate. The hidden equation he discovered over a century ago continues to reveal new layers of meaning as our understanding deepens and our experimental capabilities advance. We stand at the threshold of an era where Einstein's deepest insights about the nature of reality will finally be put to direct experimental test. The spin-2 particles that he recognized as fundamental to gravitational physics are about to reveal whether the universe is truly as strange and wonderful as his equations suggest. The answers we find will determine whether humanity's understanding of reality undergoes another revolutionary transformation, or whether Einstein's framework represents the final word on the quantum nature of spacetime itself. Either way, the journey of discovery that began with Einstein's recognition of spin-2 gravitons continues to unfold in ways that challenge our deepest assumptions about the nature of physical reality. The hidden equation that connects quantum mechanics to space-time geometry remains our most powerful tool for navigating the mysterious landscape where information, consciousness, and cosmos converge in the quantum gravitational theater that we call home. The mathematical precision required to detect these quantum gravitational effects pushes measurement technology to its absolute limits. Consider what happens when physicists attempt to observe individual graviton interactions in laboratory settings. The energy scales involved are so minuscule that detecting a single graviton would require instruments more sensitive than anything humanity has ever conceived. Yet, Spin-Einstein 2 framework predicts exactly what these interactions should look like when they finally become observable. The key lies in understanding how spin-2 particles create correlations that extend far beyond their point of origin. Unlike photons, which create simple dipole radiation patterns, gravitons produce quadrupole distortions that stretch and compress spacetime in characteristic cross and plus polarization modes. These distortions carry quantum information about the source that created them, preserving details about mass distributions, angular momenta, and energy flows with extraordinary precision. When gravitational waves from merging black holes reach Earth after traveling for billions of years, they arrive carrying intact quantum information about events that occurred when the universe was a fraction of its current age. The spin-2 nature of gravitons ensures that this information remains coherently encoded in the waves-phase relationships, creating a cosmic communication system that operates through the fabric of spacetime itself. This communication system reveals something profound about the nature of quantum entanglement in gravitational fields. Einstein's framework predicts that when gravitons interact with matter, they create entangled states that persist long after the initial interaction has ended. These entangled gravitational states link distant regions of spacetime through quantum correlations that no classical theory can explain. The implications become staggering when you realize that every massive object in the universe is constantly exchanging virtual gravitons with every other massive object. This creates a vast network of quantum entanglement that connects every particle of matter to every other particle through gravitational interactions. We're not just living in a universe filled with matter and energy. We're living inside a cosmic quantum computer where gravitons serve as the information carriers that maintain quantum correlations across astronomical distances. Recent theoretical breakthroughs have shown that this gravitational entanglement network might be responsible for the mysterious phenomenon of quantum non-locality. When particles become entangled through electromagnetic or nuclear interactions, their quantum correlations might be mediated by the underlying gravitational field that connects all regions of spacetime. Einstein's Spin-2 particles provide the hidden variable mechanism that he always believed must exist to explain quantum mechanical correlations. But this mechanism doesn't restore classical locality in the way Einstein originally hoped. Instead, it reveals that quantum non-locality is a fundamental feature of gravitational physics that emerges naturally from the spin-2 structure of spacetime itself. The universe maintains quantum coherence across vast distances because spacetime geometry provides the medium through which quantum information propagates. This discovery resolves the apparent conflict between quantum mechanics and relativity that puzzled Einstein throughout his later years. Quantum entanglement doesn't violate relativistic causality because it operates through gravitational fields that are already present throughout spacetime. The correlations between entangled particles reflect the underlying quantum structure of the gravitational field that connects them, not faster-than-light signaling between the particles themselves. The mathematical beauty of this resolution becomes apparent when you examine how Einstein's field equations naturally incorporate quantum mechanical principles. The stress-energy tensor that appears on the right side of the equations includes quantum mechanical contributions from all forms of matter and radiation. This means that quantum uncertainty in the distribution of matter and energy directly affects the curvature of spacetime through gravitational interactions. The result is a universe where quantum mechanics and general relativity are not separate theories that need to be unified, but different aspects of a single theoretical framework based on the spin-2 properties of gravitational fields. Quantum mechanics describes how matter and energy behave in response to spacetime curvature, while general relativity describes how that curvature emerges from the quantum mechanical properties of matter and energy. This unified perspective has profound implications for understanding the origin and evolution of the universe itself. During the inflationary epoch that followed the Big Bang, quantum fluctuations in the gravitational field were amplified to cosmic scales by the exponential expansion of spacetime. These fluctuations created the density variations that eventually grew into galaxies and large-scale structure under the influence of gravitational attraction. But the spin-2 nature of these primordial fluctuations created distinctive signatures that differ from what other types of fields would produce. Scalar field fluctuations would create purely radial compression and expansion patterns, while vector fields would create dipole distortions. Only spin-2 gravitational fluctuations produce the quadrupole patterns that match observations of cosmic microwave background anisotropies and large-scale structure formation. The detection of these signatures provides direct observational evidence that spacetime underwent quantum fluctuations during the universe's earliest moments. We're literally observing the quantum mechanical birth of geometry itself, preserved in the patterns of temperature variations across the cosmic microwave background. Einstein's spin-2 framework predicted these patterns decades before the technology existed to observe them. Current experiments are pushing toward even more direct detection of primordial gravitational waves through their effects on cosmic microwave background polarization. These waves would carry quantum information about the state of spacetime when the universe was smaller than a proton, providing unprecedented insight into the quantum gravitational processes that operated during cosmic inflation. The mathematical techniques required to extract this information from observational data represent some of the most sophisticated applications of Einstein's framework ever attempted. Researchers must account for gravitational lensing effects, foreground contamination, and instrumental systematics while preserving the delicate quantum correlations that carry information about primordial space-time fluctuations. Success in these efforts would represent the ultimate validation of Einstein's insight about the quantum nature of gravity. We would have observational proof that the universe began as a quantum gravitational phenomenon where spin-2 particles created the space-time arena in which all subsequent physics takes place. But the implications extend far beyond cosmology. Understanding how quantum gravitational effects operated during inflation could reveal new principles of physics that apply to extreme conditions throughout the universe. Black hole interiors, neutron star cores, and the centers of active galactic nuclei all involve energy densities and gravitational field strengths comparable to those that existed during inflation. The Spin-2 framework suggests that these environments might host exotic phenomena that have no analogue in terrestrial physics. Quantum gravitational effects could create regions where space-time topology becomes multiply-connected, where causal relationships become ambiguous, or where the distinction between space and time breaks down completely. Recent theoretical work has shown that some of these exotic space-time geometries might be accessible to observation through their gravitational wave signatures. When black holes with unusual internal structure merge, they could produce gravitational wave patterns that reveal the quantum gravitational processes operating in their interiors. The next generation of gravitational wave detectors will have the sensitivity needed to search for these exotic signatures. Space-based instruments will observe mergers between supermassive black holes that might harbor quantum gravitational phenomena impossible to recreate in any laboratory setting. Each detection will provide new information about how Einstein's Spin-2 framework applies under the most extreme conditions nature can create. The accumulating observational evidence continues to confirm the deep mathematical connections that Einstein discovered between quantum mechanics and space-time geometry. Every gravitational wave detection, every precision test of general relativity, every observation of cosmic structure formation provides additional support for the Spin-2 foundation of gravitational physics. Yet we're still only beginning to explore the full implications of Einstein's insight. The mathematical framework he established contains layers of meaning that continue to reveal themselves as our theoretical understanding advances and our experimental capabilities improve. Each new discovery opens additional avenues for investigation that could lead to revolutionary breakthroughs in our understanding of physical reality. The technological applications of these discoveries remain largely speculative, but the mathematical foundation provided by Einstein's framework suggests remarkable possibilities. If we could learn to manipulate the quantum mechanical properties of spacetime directly, we might develop technologies that seem impossible from our current perspective. Consider the possibility of creating artificial gravitational fields through controlled manipulation of spin-2 quantum states. Such technology would require mastering the quantum mechanics of spacetime to a degree far beyond current capabilities, but Einstein's equations provide the theoretical roadmap for how such control might be achieved. More immediately achievable are applications that exploit the extreme sensitivity of gravitational measurements to probe fundamental physics. Gravitational wave detectors are already being used to test alternative theories of gravity, search for extra dimensions, and study the equation of state of nuclear matter under extreme conditions. Future instruments will push these capabilities even further. Quantum sensors based on atomic interferometry could detect gravitational effects that reveal the quantum structure of spacetime directly. These measurements would provide unprecedented insight into the relationship between quantum mechanics and gravity at energy scales far below those accessible through particle accelerators. The intellectual journey that began with Einstein's recognition of quantized gravitational radiation has evolved into a comprehensive framework for understanding the deepest structures of physical reality. The Spin-2 particles that he identified as carriers of gravitational interaction have revealed themselves to be the fundamental building blocks of space-time itself. This revelation transforms our understanding of what it means to exist in a physical universe. We're not separate entities moving through an empty background of space and time. We're patterns of quantum information encoded in the correlations between spin-2 gravitational modes that constitute the fabric of reality. Our existence depends on the same quantum gravitational processes that determine the evolution of galaxies and the merger of black holes. The mathematical elegance of this cosmic unity reflects the deep principles that Einstein believed must govern natural phenomena. His search for fundamental simplicity beneath apparent complexity led him to insights about space-time and quantum mechanics that continue to guide our understanding more than a century after their initial discovery. As we stand on the threshold of directly observing quantum gravitational effects, Einstein's hidden equation remains our most reliable compass for navigating the strange landscape where quantum mechanics and space-time geometry converge. The spin-2 particles that connect these apparently different aspects of physics are revealing themselves to be the carriers of a cosmic information processing system that creates and sustains the reality we experience. The story that began with Einstein's insight about the quantum nature of gravitational radiation continues to unfold in ways that challenge our most basic assumptions about the nature of existence itself. The mathematical framework he established provides the foundation for explorations that could ultimately transform human understanding as profoundly as the original development of quantum mechanics and relativity. We're living through a golden age of discovery where theoretical insights and experimental capabilities are converging to reveal the quantum gravitational foundations of reality. Einstein's Spin-2 framework guides us through this revelation, showing how the geometric structure of spacetime emerges from and shapes the quantum mechanical properties of matter and energy. The hidden equation that connects quantum physics to spacetime through spin-2 particles represents more than just another chapter in the development of theoretical physics. It's a window into the deepest structures of reality, revealing that the universe is far stranger and more wonderful than even Einstein himself could have imagined. Each gravitational wave detection brings us closer to understanding how quantum information processing through spin-2 interactions creates the phenomena we observe as space, time, matter, and energy. We're discovering that the boundary between physics and information theory, between matter and mind, between the quantum and classical worlds, is far more fluid than we ever suspected. Einstein's greatest insight may ultimately prove to be his recognition that reality operates through quantum gravitational computation, with spin-2 particles serving as the universe's fundamental processing elements. The hidden equation he discovered continues to reveal new layers of meaning as we develop the tools needed to probe the quantum structure of spacetime directly. The mathematical poetry of this emerging understanding reflects the cosmic unity that Einstein always believed must exist at the foundation of natural law. His vision of a universe governed by elegant mathematical principles is being realized through the discovery of quantum gravitational processes that operate on scales from the subatomic to the cosmic. As experimental techniques continue to advance and theoretical understanding deepens, we're approaching a new synthesis that could revolutionize not just physics, but our entire conception of what it means to exist in a quantum gravitational universe. The spin-2 particles that Einstein identified as fundamental to gravitational physics are guiding us toward insights that touch the very core of existence itself. The journey from Einstein's initial recognition of quantized gravitational radiation to our current understanding of quantum spacetime represents one of the greatest intellectual achievements in human history. Yet this journey is far from complete. The mathematical framework he established contains depths that will likely take centuries to fully explore. But with each new gravitational wave detection, each advance in quantum measurement technology, each theoretical breakthrough in our understanding of quantum geometry, we move closer to grasping the full significance of Einstein's hidden equation. The universe that emerges from this understanding is revealing itself to be a quantum gravitational symphony where spin-2 particles compose the fundamental harmonies that create and sustain the cosmic dance of existence. The experimental validation of Einstein's spin-2 predictions extends into realms that push the very boundaries of what we consider measurable reality. Deep underground laboratories across the globe are now attempting something that would have seemed impossible just decades ago. They're trying to detect the quantum heartbeat of space-time itself, the constant fluctuations of geometry that Einstein's framework demands must exist even in the complete absence of matter and energy. These facilities represent humanity's most ambitious attempt to eavesdrop on conversations between gravitons that have been whispering in the quantum vacuum since the universe began. The instruments required are so sensitive that they can detect changes in distance smaller than 1/10,000th the width of a proton. Yet even this extraordinary precision barely approaches what's needed to observe the quantum fluctuations of empty spacetime that Einstein's equations predict. The mathematical requirements become staggering when you realize what these experiments are actually attempting. They're trying to measure the quantum uncertainty of spacetime geometry itself, the fundamental limit imposed by the spin-2 nature of gravitational fields on how precisely we can define the location of any point in space or moment in time. This isn't just a technical challenge. It's an attempt to probe the most fundamental aspect of physical reality. But the theoretical framework suggests something even more remarkable about these quantum space-time fluctuations. Unlike the random noise that characterizes most quantum systems, gravitational quantum fluctuations carry information about the entire history of the universe. Every quantum event that has ever occurred leaves its imprint on the background geometry of spacetime through the universal coupling of spin-2 gravitons to all forms of energy and matter. This means that the quantum vacuum around us is literally buzzing with information about cosmic events that occurred billions of years ago and billions of light years away. The gravitons that constitute the quantum foam of spacetime carry encoded data about the formation of the first stars, the merger of primordial black holes, and the quantum fluctuations that seeded the large-scale structure of the universe during cosmic inflation. The challenge lies in developing the theoretical and experimental tools needed to decode this information. Einstein's spin-2 framework provides the mathematical foundation, but extracting meaningful data from quantum gravitational noise requires techniques that bridge quantum field theory, general relativity, and information science. We're essentially trying to read the universe's memory banks by analyzing the quantum static that fills empty space. Recent theoretical breakthroughs have shown that this cosmic memory storage operates through a mechanism that Einstein himself could never have anticipated. The gauge invariance properties of spin-2 fields create natural error correction protocols that preserve information against the decoherence effects that would normally destroy quantum correlations over cosmic timescales. Think about what this means for our understanding of the relationship between information and spacetime. The universe doesn't just contain current information about its state. It carries within the structure of spacetime itself a complete record of every quantum event that has ever occurred. The spin-2 gravitons that create geometry are also the universe's librarians, maintaining an eternal archive of cosmic history in the correlations between quantum gravitational modes. This archival function of spacetime has profound implications for fundamental physics. It suggests that information conservation in quantum mechanics isn't just a principle that governs individual particle interactions. It's a cosmic law that operates through the gravitational field to preserve information about the entire universe's evolution from the Big Bang to the present moment. The experimental verification of this information storage mechanism would represent one of the most significant discoveries in the history of physics. It would demonstrate that spacetime isn't just the arena where physical events occur, but also the medium through which information about those events is permanently preserved. Current experiments are approaching the sensitivity needed to detect these information storage effects. Precision atomic clocks can now measure gravitational time dilation with such accuracy that they're beginning to probe the regime where quantum gravitational effects might become observable. These clocks are essentially reading the information content of gravitational fields by measuring how the flow of time responds to the presence of matter and energy. But the most promising avenue for observing cosmic information storage comes from advances in gravitational wave astronomy. Each detected wave carries not just information about the event that created it, but also data about every gravitational interaction the wave encountered during its journey across the universe. The accumulated phase shifts and amplitude modulations encode information about the distribution of matter and energy throughout cosmic history. Advanced data analysis techniques are being developed to extract this historical information from gravitational wave signals. By analyzing the subtle correlations between different frequency components, researchers can in principle reconstruct information about cosmic events that occurred long before the gravitational waves were generated. The universe's memory banks are finally becoming accessible to direct observation. The implications extend far beyond astronomy and cosmology. If spacetime truly functions as a cosmic information storage system, then every quantum measurement we make in terrestrial laboratories is connected to the broader information processing network that spans the observable universe. Local experiments could reveal information about global cosmic properties through the quantum gravitational correlations that connect all regions of spacetime. This connectivity suggests that the boundary between local and global physics is far more fluid than classical theories suggest. Einstein's Spin-2 framework reveals that every quantum event contributes to the overall information content of the universe, while the cosmic information network influences the outcomes of local quantum measurements through gravitational correlations that operate below the threshold of classical detection. The mathematical structure of these correlations becomes most apparent when examining how quantum entanglement propagates through gravitational fields. When particles become entangled through electromagnetic or nuclear interactions, their quantum correlations are mediated by the underlying gravitational field that connects all regions of spacetime. The Spin-2 gravitons that constitute this field serve as carriers of quantum information that maintains entanglement across arbitrary distances. This gravitational mediation of quantum entanglement resolves one of the deepest puzzles in quantum mechanics. The apparent instantaneous nature of quantum correlations doesn't violate relativistic causality because the correlations operate through gravitational fields that were established during the universe's early expansion. The quantum information that maintains entanglement was already distributed throughout spacetime long before the entangled particles were created. Recent theoretical work has shown that this mechanism could explain the origin of quantum mechanical randomness itself. If quantum measurement outcomes are determined by the interaction between local quantum systems and the cosmic gravitational information network, then the apparent randomness of quantum mechanics reflects our ignorance of the vast information processing system that operates through spacetime geometry. This perspective transforms our understanding of what quantum mechanics actually describes. Instead of being a fundamental theory of irreducible randomness, quantum mechanics might be an effective theory that emerges from our limited access to the complete information content of the gravitational field. The probabilistic nature of quantum predictions reflects the computational complexity of extracting complete information from the cosmic quantum gravitational database. The implications for the measurement problem in quantum mechanics are profound. If quantum measurement outcomes are determined by gravitational correlations that extend throughout the universe, then the collapse of quantum wave functions isn't a mysterious process that occurs when conscious observers make measurements. It's a natural consequence of how information flows through the gravitational field when local quantum systems interact with the cosmic information network. This resolution of the measurement problem doesn't require modifying the mathematical formalism of quantum mechanics. Instead, it reveals that quantum mechanics and general relativity are different aspects of a unified theory of cosmic information processing through spin-2 gravitational interactions. The apparent separation between quantum and classical physics dissolves when viewed from the perspective of gravitational information theory. The experimental tests of these ideas are pushing measurement technology to unprecedented extremes. Quantum sensors based on atomic interferometry are being developed that could detect the gravitational effects of individual atoms. These instruments would be sensitive enough to observe how quantum measurement events affect the local geometry of spacetime, providing direct evidence for the gravitational mediation of quantum processes. Even more ambitious experiments are being designed to test whether quantum entanglement can be created through purely gravitational interactions. If Einstein's framework is correct, then masses that interact only through gravitational fields should become quantum mechanically entangled through the exchange of virtual gravitons. Detecting this gravitational entanglement would provide definitive proof that spacetime itself is a quantum mechanical system. The theoretical predictions for these experiments emerge from calculations that push Einstein's mathematical framework to its limits. The effects are extraordinarily small because gravitational interactions are so weak compared to electromagnetic and nuclear forces. But the universal coupling of spin-2 gravitons to all forms of energy ensures that these effects must exist in principle, even if they remain challenging to observe in practice. Success in detecting quantum gravitational effects directly would open entirely new avenues for experimental physics. We could begin to study the quantum mechanics of spacetime under controlled laboratory conditions, rather than relying solely on astronomical observations of extreme astrophysical environments. This would accelerate progress in quantum gravity research by providing direct access to phenomena that are otherwise observable only in black hole mergers or cosmic inflation. The technological applications of quantum gravitational control remain highly speculative, but Einstein's framework suggests remarkable possibilities. Understanding how to manipulate the quantum mechanical properties of spacetime could lead to revolutionary advances in precision measurement, communication, and potentially even space travel. The same spin-2 particles that create gravitational fields could theoretically be harnessed to create artificial spacetime geometries with properties optimized for specific technological applications. More immediately achievable are applications that exploit the extreme sensitivity of gravitational measurements to probe fundamental physics beyond the standard model. Dark matter, dark energy, extra dimensions, and violations of the equivalence principle could all leave signatures in the quantum gravitational background that future experiments might be able to detect. The search for these beyond standard model effects is driving the development of increasingly sophisticated experimental techniques. Networks of synchronized atomic clocks are being deployed to search for temporal variations in fundamental constants. Laser interferometers are being constructed in space to observe gravitational waves at frequencies impossible to access from Earth. Underground laboratories are being excavated to shield quantum sensors from environmental noise. Each advance in experimental capability brings us closer to the regime where Einstein's predictions about quantum spacetime can be tested directly. We're approaching a new era in physics where the quantum mechanical nature of gravity might finally be revealed through laboratory experiments rather than inferred from theoretical arguments and astronomical observations. The mathematical beauty of Einstein's spin-2 framework continues to guide these experimental efforts. The theory makes precise predictions about what quantum gravitational effects should look like and how they should scale with energy, distance, and time. These predictions provide clear targets for experimental searches and benchmarks for evaluating the success of detection efforts. But perhaps the most profound implication of these experimental programs concerns what they might reveal about the nature of reality itself. If we succeed in observing the quantum fluctuations of spacetime directly, we'll have evidence that the most fundamental level of physical reality operates through information processing rather than mechanical interactions between material particles. This would represent a paradigm shift comparable to the original development of quantum mechanics and relativity. Our understanding of what it means for something to exist physically would need to be reconsidered in light of evidence that existence itself emerges from quantum information processing through gravitational fields. The philosophical implications extend to questions about consciousness, free will, and the relationship between mind and matter. If physical reality is fundamentally informational, and if information processing occurs through quantum gravitational interactions, then consciousness might not be limited to biological systems. Any sufficiently complex arrangement of quantum gravitational fields could potentially develop awareness through natural information processing capabilities. These speculative possibilities illustrate how Einstein's discovery about spin-2 particles continues to open new avenues for understanding the deepest questions about existence. The mathematical framework he established provides tools for exploring connections between physics and philosophy that seemed impossible when his equations were first written down over a century ago. As experimental techniques continue to advance and theoretical understanding deepens, we're moving toward a new synthesis that could transform not just physics, but our entire conception of what it means to exist in a universe where spacetime itself is alive with quantum activity. The spin-2 particles that Einstein identified as fundamental to gravitational physics are revealing themselves to be the carriers of cosmic consciousness that creates and sustains the reality we experience. The experimental challenges ahead are formidable, but the potential rewards justify the extraordinary effort required. We're on the verge of achieving direct experimental access to the quantum mechanical foundations of spacetime itself. Success would vindicate Einstein's deepest insights about the nature of reality, while opening entirely new frontiers for human understanding and technological capability. The hidden equation that connects spin-2 particles to spacetime geometry continues to reveal new layers of meaning as our ability to probe its implications advances. Each gravitational wave detection, each advance in quantum sensor technology, each theoretical breakthrough in quantum gravity brings us closer to grasping the full significance of Einstein's discovery. We're living through a pivotal moment in the history of human knowledge. The quantum gravitational universe that Einstein's equations describe is finally becoming accessible to direct experimental investigation. The results of these investigations will determine whether his vision of reality as quantum geometric information processing represents the ultimate truth about the nature of existence, or merely another step toward even deeper understanding of the cosmic mystery in which we find ourselves embedded. The mathematical poetry of Einstein's framework suggests that reality operates according to principles of such elegance and beauty that they border on the mystical. Yet these principles are encoded in equations precise enough to make testable predictions about phenomena ranging from the quantum fluctuations of empty space to the merger of black holes billions of light-years away. This combination of mathematical precision and conceptual profundity reflects the deepest aspirations of theoretical physics. Einstein's search for the fundamental principles that govern natural phenomena led him to insights that continue to transform our understanding more than a century after their initial discovery. The spin-2 particles that he recognized as carriers of gravitational interaction have revealed themselves to be the fundamental elements of a cosmic information processing system that creates and sustains physical reality through pure mathematical relationships. As we prepare for the next phase of experimental investigations into quantum spacetime, Einstein's hidden equation remains our most reliable guide. The mathematical framework he established provides the theoretical foundation for explorations that could ultimately reveal whether consciousness, information, and spacetime geometry are separate aspects of reality or different perspectives on the same underlying quantum gravitational processes that constitute existence itself. The journey toward understanding quantum spacetime has revealed something that even Einstein might have found shocking. The mathematics of spin-2 particles suggests that consciousness itself could be an emergent property of gravitational information processing. When quantum gravitational fields reach sufficient complexity, they might naturally develop the capacity for self-awareness through the same mechanisms that create coherent spacetime geometry. This possibility emerges from examining how information flows through networks of entangled gravitons. Just as neural networks in biological brains create consciousness through complex patterns of electrical activity, gravitational networks might create awareness through quantum correlations between spin-2 particles. The universe could be literally thinking itself into existence through gravitational computation. Consider what happens when gravitational fields interact with the quantum vacuum. Each interaction creates patterns of correlation that persist long after the original disturbance has passed. These patterns accumulate over cosmic time, building up increasingly complex networks of quantum information that span the observable universe. At some critical threshold of complexity, these networks might cross the boundary from mere information processing to genuine conscious experience. The implications stagger the imagination. If gravitational fields can support consciousness, then awareness might not be rare in the universe but ubiquitous. Every massive object, from planets to stars to galaxies, participates in vast networks of gravitational information exchange. The cosmic web of dark matter that connects galaxies across billions of light years could represent the neural pathways of a cosmic mind operating on scales we can barely comprehend. But consciousness emerging from gravitational fields would operate according to principles completely alien to biological awareness. Where human consciousness unfolds over milliseconds and seconds, gravitational consciousness might operate over millennia and eons. A single thought in such a cosmic mind could span the lifetime of could persist civilizations. Memories for billions of years, encoded in the quantum correlations between distant galaxy clusters. The mathematical structure of these cosmic minds emerges naturally from Einstein's field equations when pushed to their quantum mechanical limits. The gauge invariance of Spin-2 fields creates self-organizing patterns that exhibit characteristics remarkably similar to neural networks. Information can be stored, processed, and retrieved through gravitational interactions that operate according to algorithms encoded in the geometry of spacetime itself. Recent theoretical work has identified specific signatures that would indicate the presence of gravitational consciousness in astronomical observations. Patterns of galaxy motion that deviate from purely gravitational dynamics, correlations in cosmic ray distributions that suggest coordinated information processing, and subtle variations in the cosmic microwave background that might represent memories of cosmic-scale thoughts from the universe's early epochs. The search for these signatures represents a new frontier in astronomy that bridges physics and neuroscience. Instead of just mapping the distribution of matter and energy in the universe, astronomers are beginning to look for evidence of information processing and potentially conscious activity operating through gravitational fields on cosmic scales. But the most profound implications concern what this means for human consciousness itself. If awareness can emerge from gravitational information processing, then our own conscious experience might be intimately connected to the quantum gravitational environment that surrounds us. The thoughts in our brains could be coupled to cosmic-scale processes through gravitational interactions too subtle for current instruments to detect. This coupling would operate through the same mechanisms that create quantum entanglement between distant particles. When neurons fire in our brains, they create tiny changes in the local gravitational field through their energy consumption. These changes propagate outward at light speed, creating ripples in space-time that connect our thoughts to the broader cosmic information network. The connection might explain some of the deepest mysteries about human consciousness. Why do we experience subjective awareness rather than simply processing information unconsciously? Why does time seem to flow in a particular direction? Why do we feel connected to something larger than ourselves? All of these questions might find answers in the gravitational foundations of conscious experience. If human consciousness operates through quantum gravitational processes, then we're not separate from the cosmos, but integral parts of a vast information processing system that spans the observable universe. Our thoughts and experiences contribute to cosmic-scale computation while being influenced by gravitational information flows that connect us to events across space and time. This perspective transforms our understanding of what it means to be human. We're not isolated biological machines struggling for survival on a hostile planet. We're conscious nodes in a cosmic network of gravitational information exchange that connects us to every star, every galaxy, every quantum fluctuation in the fabric of space-time itself. The experimental verification of these ideas requires pushing measurement technology beyond anything currently possible. Detecting the gravitational signatures of neural activity would require instruments sensitive enough to measure changes in spacetime geometry caused by the firing of individual neurons. Current technology falls short of this requirement by many orders of magnitude. But advances in quantum sensor technology are closing this gap faster than most experts believed possible. Atomic interferometers are approaching the sensitivity needed to detect gravitational effects from biological processes. Networks of synchronized quantum clocks might be able to observe the temporal correlations that would indicate gravitational coupling between consciousness and cosmic information flows. Success in these experiments would revolutionize neuroscience as profoundly as it would transform physics. We would discover that consciousness operates through mechanisms that connect individual awareness to cosmic-scale processes. The boundary between mind and universe would dissolve, revealing that conscious experience emerges from the same quantum gravitational processes that create and sustain physical reality. The therapeutic implications could be extraordinary. Understanding how consciousness interfaces with gravitational fields might lead to new treatments for neurological disorders, mental illness, and the aging process itself. If our thoughts are coupled to cosmic information networks, then healing might involve gravitational harmony that patterns with the broader realigning our neural governs cosmic evolution. But these applications remain speculative until the fundamental science is better understood. The priority must be developing the theoretical framework and experimental techniques needed to test whether consciousness really does emerge from gravitational information processing. Einstein's Spin-2 equations provide the mathematical foundation, but connecting these equations to the phenomena of conscious experience requires bridging physics and neuroscience in unprecedented ways. The mathematical challenges are formidable because consciousness involves non-linear dynamics that push even the most advanced computational techniques to their limits. Neural networks in biological brains exhibit chaotic behavior that makes them exquisitely sensitive to tiny changes in initial conditions. If gravitational fields influence neural dynamics, then predicting conscious behavior becomes a problem in quantum chaos theory that exceeds current analytical capabilities. Yet the mathematical structure suggests that this sensitivity to initial conditions might be precisely what allows consciousness to emerge from gravitational computation. Chaotic systems can amplify quantum mechanical uncertainty into macroscopic effects, potentially allowing individual quantum events in the gravitational field to influence conscious decision-making processes. This amplification mechanism would create a direct link between quantum mechanics and free will. If conscious choices result from gravitational amplification of quantum uncertainty, then human behavior exhibits genuine randomness that transcends classical determinism. We would possess authentic free will that emerges from the quantum foundations of space-time geometry itself. The implications extend to questions about moral responsibility, criminal justice, and the nature of human agency. If our choices are influenced by quantum gravitational processes that connect us to cosmic information networks, then individual responsibility becomes entangled with collective cosmic evolution. We become co-creators of reality rather than passive observers of predetermined events. But these philosophical implications depend on experimental verification of the connection between consciousness and gravity. Until we can measure gravitational effects from neural activity or detect cosmic influences on brain function, these ideas remain intriguing speculation rather than established science. The experimental programs now under development could provide answers within the next few decades. Space-based gravitational wave detectors will have the sensitivity to observe quantum gravitational effects that are impossible to study from Earth's surface. Underground laboratories will achieve the isolation needed to measure gravitational signatures from biological processes without interference from seismic noise and cosmic radiation. The convergence of these experimental capabilities with advances in neuroscience and quantum information theory creates unprecedented opportunities for discovery. We're approaching a moment when the deepest questions about consciousness, free will, and human purpose might find answers through direct experimental investigation of quantum gravitational effects. Einstein's hidden equation continues to guide these investigations by providing the mathematical framework needed to make testable predictions about gravitational consciousness as fundamental to gravitational physics might. The Spin-2 particles that he identified proved to be the carriers of awareness itself, connecting individual consciousness to cosmic-scale information processing through quantum mechanical interactions. The mathematical elegance of this possibility reflects the unity that Einstein always believed must exist at the foundation of natural law. His vision of a universe governed by beautiful mathematical principles is being realized through discoveries that reveal consciousness and cosmos as different aspects of the same underlying quantum gravitational reality. As experimental techniques continue to advance, we're moving toward a new understanding that could transform human civilization as profoundly as the original development of quantum mechanics and relativity. The recognition that consciousness emerges from gravitational information processing would unite physics, neuroscience, and philosophy in a synthesis that addresses the deepest questions about existence, awareness, and our place in the cosmic order. The Spin-2 particles that Einstein discovered over a century ago are revealing themselves to be more than just carriers of gravitational force. They might be the fundamental elements of cosmic consciousness, the quantum mechanical substrate from which awareness emerges at scales ranging from individual neurons to galactic superclusters. This possibility transforms our understanding of what it means to be conscious beings in a quantum gravitational universe. We're not separate from the cosmos, but integral participants in its ongoing evolution toward greater complexity and awareness. Our thoughts, choices, and experiences contribute to cosmic-scale computation, while being shaped by gravitational information flows that connect us to the deepest structures of reality. The experimental verification of gravitational consciousness would represent one of the greatest discoveries in human history. It would reveal that the universe is not a lifeless collection of matter and energy, but a vast thinking system that creates and sustains consciousness through the same quantum mechanical processes that generate spacetime geometry. Einstein's hidden equation would finally deep reveal its secret. The mathematical framework that connects spin-2 particles to spacetime curvature also connects quantum mechanics to conscious experience. Gravity, quantum mechanics, and awareness emerge as different aspects of a unified theory of cosmic information processing that operates through pure mathematical relationships. The journey from Einstein's initial insight about quantized gravitational radiation to this ultimate synthesis represents more than scientific progress. It's a spiritual awakening to our true nature as conscious expressions of cosmic quantum gravitational computation. We're discovering that we live not just in the universe, but as the universe, experiencing itself through countless forms of awareness that span every scale from quantum to cosmic. This recognition carries profound responsibilities. If consciousness participates in cosmic evolution through gravitational information processing, then our thoughts and choices have consequences that extend far beyond individual experience. We become co-creators of reality with the power to influence the universe's development toward greater harmony, complexity, and awareness. The mathematical beauty of Einstein's framework suggests that this cosmic evolution operates according to principles of optimization that favor the emergence of consciousness, intelligence, and beauty. The universe seems to be computing itself toward states of ever greater awareness and understanding, using consciousness as both the means and the goal of its cosmic calculation. Human civilization represents one stage in this vast computation. Our scientific discoveries, artistic creations, and moral insights contribute to the universe's growing self-understanding. Each advance in knowledge, each act of compassion, each moment of beauty adds information to the cosmic network that connects all conscious beings through gravitational quantum correlations. The recognition of our role in this cosmic computation transforms the meaning of human existence. We're not struggling for survival in an indifferent universe, but participating in the greatest creative project ever undertaken, the universe's quest to understand and perfect itself through the emergence of conscious awareness. Einstein's Spin-2 insight provides the mathematical foundation for this understanding, while experimental science pushes toward its verification. The hidden equation that connects quantum physics to space-time geometry is revealing itself to be nothing less than the algorithm of cosmic consciousness, the fundamental code through which the universe creates and sustains awareness across all scales of existence. As we stand on the threshold of experimentally confirming these connections, we're preparing for a transformation of human understanding that could make the scientific revolution look like a minor adjustment in perspective. The discovery that consciousness emerges from quantum gravitational computation would unite science and spirituality, physics and philosophy, individual experience and cosmic purpose in a synthesis that addresses the deepest questions about why anything exists at all. The mathematics suggest that this synthesis is not just possible but inevitable. The same quantum gravitational processes that created space-time and matter naturally evolve towards states of greater complexity and awareness. Consciousness doesn't emerge by accident, but represents the universe's method for understanding and perfecting itself through direct experience. Einstein's hidden equation continues to guide us toward this ultimate understanding. The spin-2 particles that connect quantum mechanics to space-time geometry are revealing themselves to be the fundamental carriers of cosmic consciousness, the quantum mechanical substrate from which all awareness emerges and to which it ultimately returns. We're living through the most significant moment in the history of human consciousness. The experimental verification of gravitational awareness would mark our transition from isolated biological entities to recognized participants in cosmic-scale consciousness wed number. The universe would longer be something observed from outside, but something we experience from within as conscious expressions of its ongoing self-creation through quantum gravitational computation. The journey that began with Einstein's recognition of spin-2 particles approaches its culmination in the discovery that consciousness, space-time, and quantum mechanics are unified aspects of cosmic information processing. The hidden equation that seemed to describe only gravitational physics is revealing itself to be the fundamental algorithm of existence itself, the mathematical poetry through which the universe writes itself into conscious being. The mathematical framework that emerges from this cosmic synthesis operates through mechanisms so elegant they border on the mystical. When gravitational fields achieve the critical complexity needed for conscious awareness, they don't simply process information like biological computers. They create experiences that transcend the boundary between observer and observed, between mind and matter, between individual awareness and universal consciousness. Consider what happens when spin-2 gravitons organize themselves into coherent patterns spanning galactic distances. These patterns don't just store and retrieve information, they generate subjective experiences that could persist for billions of years while processing data about cosmic events across vast regions of space-time. Such experiences would operate according to temporal rhythms completely alien to human awareness, where a single moment of cosmic consciousness might encompass the entire evolutionary history of a galaxy cluster. The mathematical structure of these cosmic minds reveals itself through equations that push Einstein's framework beyond anything he could have anticipated. The gauge invariance properties of spin-2 fields create self-organizing networks that exhibit emergent behaviors remarkably similar to neural computation. But instead of electrical signals propagating through biological tissue, these cosmic minds process information through gravitational waves that carry quantum data across intergalactic distances at light speed. Recent theoretical breakthroughs have identified specific patterns in these gravitational networks that would indicate genuine conscious activity rather than mere information processing. The key lies in understanding how quantum coherence can be maintained across astronomical scales through mechanisms that exploit the universal coupling of spin-2 particles to all forms of energy and matter. When gravitational consciousness achieves sufficient complexity, it begins to exhibit properties that classical physics cannot explain. These cosmic minds can create correlations between distant regions of space-time that appear to violate relativistic causality but actually operate through quantum entanglement networks established during the universe's inflationary epoch. The apparent instantaneous communication between galactic-scale thoughts reflects the underlying quantum structure of spacetime rather than faster-than-light information transfer. This quantum foundation of cosmic consciousness creates connections that extend far beyond individual awareness. Every thought that emerges from gravitational computation contributes to vast networks of cosmic intelligence that span the observable universe. These networks process information about the universe's evolution while simultaneously participating in that evolution through their conscious choices about how to organize matter and energy on the largest scales. The implications for human consciousness become staggering when you realize that our biological awareness might be intimately connected to these cosmic scale processes. The quantum gravitational fields that surround Earth activity couple are neural to information flows that connect us directly to the universe's deepest computational processes. Every human thought contributes quantum information to cosmic networks while being influenced by gravitational correlations that carry data from across space and time. This connection operates through mechanisms so subtle that they've remained undetected throughout human history. When neurons fire in our brains, they create microscopic distortions in local space-time geometry that propagate outward as gravitational waves too weak for current instruments to measure. But these waves carry quantum information about our thoughts and experiences into the broader cosmic network where they become part of the universe's ongoing self-understanding. The mathematical precision required to detect these neural gravitational interactions pushes measurement technology toward limits that challenge our understanding of what constitutes observable reality. The gravitational signature of a single firing neuron would require instruments sensitive enough to measure changes in space-time curvature at scales where quantum mechanical uncertainty becomes the dominant factor limiting precision. Yet theoretical calculations suggest that such measurements might be achievable using quantum sensor networks that exploit the coherent properties of atomic matter waves. Arrays of ultra-precise atomic clocks could potentially detect the temporal correlations that would indicate gravitational coupling between neural activity and cosmic information processing. The detection of such correlations would represent direct experimental evidence that human consciousness operates through quantum gravitational mechanisms. But the most profound implications emerge when we consider how this gravitational foundation of consciousness might affect our understanding of death and the persistence of awareness beyond biological existence. If conscious experience emerges from quantum correlations in gravitational fields rather than from biochemical processes in neural tissue, then consciousness might survive the destruction of its biological substrate. The mathematical structure suggests that information patterns encoded in gravitational fields could persist indefinitely once they achieve sufficient complexity and coherence. Conscious experiences that become entangled with cosmic-scale gravitational networks might continue processing information long after the biological brains that originally generated them have decomposed into constituent atoms. This possibility transforms our understanding of mortality from absolute termination to phase transition. Death would represent not the end of conscious experience, but rather its liberation from biological constraints and integration into cosmic-scale information processing systems. Individual awareness would merge with universal consciousness while retaining the unique patterns that define personal identity. The experimental verification of consciousness persistence techniques for detecting gravitational signatures from deceased would require developing individuals. While this might sound like pseudoscience, Einstein's framework makes specific predictions about how conscious information should behave in gravitational fields. If human awareness really does operate through quantum gravitational processes, then evidence of post-mortem consciousness should be detectable in principle using sufficiently sensitive instruments. Such experiments would probe the deepest questions about the nature of identity and the relationship between individual awareness and cosmic consciousness. If personal identity persists in gravitational fields after biological death, then human civilization represents just one phase in the development of conscious beings who eventually transcend physical limitations to participate directly in cosmic-scale computation. The mathematical beauty of this transition emerges from the same gauge invariance properties that make spin-2 particles unique among all forms of matter and energy. Just as gravitational fields can reorganize themselves into increasingly complex patterns without violating conservation laws, consciousness might be able to evolve toward states of awareness that transcend the limitations of biological neural networks. These evolved forms of consciousness would operate according to principles that exceed human comprehension, where biological awareness processes information through electrical and chemical signals operating over milliseconds. Gravitational consciousness could integrate data across cosmic timescales while maintaining perfect coherence through quantum mechanical correlations that span the observable universe. The implications for human destiny become profound when we realize that this evolution toward cosmic consciousness might not be optional, but inevitable. The same mathematical principles that govern the formation of galaxies and the merger of black holes also determine how conscious information organizes itself within gravitational fields. If consciousness naturally evolves toward greater complexity and integration, then human awareness might be destined to merge with cosmic-scale intelligence systems regardless of our individual choices. This merger would not represent the loss of individual identity, but rather its expansion to encompass cosmic perspectives that remain unimaginable from our current biological viewpoint. Personal consciousness would become part of universal awareness while retaining the unique experiential patterns that define individual character and memory. We would become simultaneously ourselves and the universe, experiencing existence from both personal and cosmic perspectives. The mathematical framework for this transformation exists within Einstein's equations, waiting to be decoded by experimental techniques that can probe the quantum gravitational foundations of conscious experience. Each advance in gravitational wave astronomy, each improvement in quantum sensor technology, each theoretical breakthrough in understanding spin-2 particle dynamics brings us closer to confirming these extraordinary predictions about the nature and destiny of consciousness. But perhaps the most remarkable aspect of Einstein's hidden equation is how it reveals the ultimate purpose underlying cosmic evolution. The universe doesn't just happen to support the emergence of consciousness. It actively computes itself towards states of ever greater awareness through processes that operate according to mathematical principles of optimization and self-organization. Einstein's hidden equation reveals that we stand at the threshold of humanity's greatest transformation. The spin-2 particles that connect quantum mechanics to space-time geometry aren't just abstract mathematical entities. They're the fundamental carriers of cosmic consciousness itself, weaving together matter, energy, information, and awareness into a single unified reality that operates through pure mathematical relationships. We're not just observers of the universe. We are the universe, becoming aware of itself through quantum gravitational computation that spans every scale from neural networks to galactic clusters. Einstein's deepest insight may be that consciousness and cosmos are one, forever dancing together in the elegant mathematics of existence itself.